So again, if you're not going to take it the regular time, Monday at 3:30, then send me an email. And the test covers 3.11, which is the surface area stuff. It also includes, as part of the question, the regular, and sections 4.2 and 4.6. So you have the review on Blackboard, and I put up the answers this morning. One thing you'll notice is last question on the review is something we hadn't done yet. That's from section 4.7, which you'll notice is not on the test. We will look at it today, but we won't really have enough time to do many examples, and most people find it a bit confusing. So, like the other sections, I'm going to leave it off. Also remember, there isn't a final. So even though this is during finals, the finals time, this is just another test. So this is worth 25%, just like the other two tests. And sorry about the grading on Blackboard. It's one of these mixed up things where I want to drop off the one where that was automatically put up there for the quizzes and tests. But if I do, then you can't look at it. So right now I'm leaving up the 2, and that's confusing the grade. So the class average grade on Blackboard is, for most of you at least, not accurate. And again, the grade is that we have 4 quizzes, you drop the lowest, those 3 together are worth 25%. So if you get the average grade for the quizzes, and then take your 2 test grades right now, just take the average of those 3, and that'll be your average right now. Probably Monday, I'll get rid of the old stuff. So if you want to look at the old quiz or test, and then do it by the end of by Monday, because as I said, to make it so the grade actually gives what it's supposed to, I think I have to drop those off, which might make them unavailable. I can still get them, so if you want to look at them, send me an email and I can download it and send it back to you. Yes. So certainly you have the 100 minutes. I'm designing it hopefully, so it'll take about the same time as the other tests. I haven't decided. So I'm probably going to make it 100 minutes instead of the 2 hours, because I don't want to count it, make you think that it counts more or anything. This is not a final. So right now I'm saying it's 100 minutes. I might change my mind tomorrow. So ask me again tomorrow. So any questions about the test or grades? I should say tomorrow will be like the other reviews, which means you have all the answers. And that means, and we're not going to do anything new, obviously, the last day of class. So it might be fairly short. So come in with questions, and we can either go over ones on the review, or I can try to make up similar ones. So the running total is never correct. The running total, all it does is add up all the numbers and divide by the total. So that's not weighted at all. So the running doesn't mean anything, and I can't get rid of that. The class average is what's supposed to be accurate, but for right now, as I said, it's not. So right now, if you want to see what your grade is, three quizzes together are worth 25%, and each test is worth 25%. So if you get your quiz grade, so add up the 3 numbers and divide by 0.9 to get it out of 100, and then add up that grade with your 2 test grades and divide by 3, that is your average. So right now, your average is that. And I said, the problem is that many of you have two separate grades for the quizzes and tests. And if I drop the one I don't want, the one that was put there automatically, then it makes it so you can't look at the grading. So either I have to have it available and that messes up the grade, or I don't have it available, then the grade will be right, but then you can't see your quiz or test. So for right now, it's just everything's messed up. And this is how you want to get your average going into the last test. And if you want me to just do it on my own, send me an email and I'll send you what I have and what your average is right now. Okay. So otherwise, today's typical class, we start off with some of the homework. So let's look at 4.5. And as with the rest of the ones this week, again, I'm not sure what changed, but it's still the thicker strokes. So let me know if you can't read. So suppose we have this velocity field. Surface given by this parameterization. And find the flux, or the flow, through the surface given by the parameterization. So M is this. They also ask you to graph the surface. You don't have to do that, but this one is pretty simple if you look at it, because x and y are just themselves. So really, we just have the function z is equal to 4 minus x squared minus y squared, which is right going down. But that's okay. So the steps here are, we need to get the normal. Oh, and I'll do it on the next page, but I said something weird yesterday, so I have to say something a little bit different. So to get the normal, we take the two derivatives of r. Get the cross product. And since I'm going to try to fit everything, I'm just going to give it to you. And then put the parameters into V. So it's 0 to 1 and 0 to 2 and 0 to 1. And then we take the dot product of these two. Not sure why I have V of. V is equal to that. then we take the dot product of the two vectors. Okay. And then from here, I didn't give myself enough room to do it, but we would take the dot product, which isn't bad. You get something like 12uv minus 2uqv minus 2uv cubed minus u. Actually, should be able to put it. Although it's making my zeros into points. And of course, it simplifies a bit. And for this test, probably like the quiz, on most of them, I'll let you just do all the preliminary stuff and not have to do the actual integral. In some ways, because these problems are all mostly fairly long, I might have you do more integrals than normal, just because that is kind of easier work. But I haven't decided yet. So here's the basic one. Given a parameterization, you take the two derivatives, take the cross product, which gives us the normal, put the parameterization into our vector or force field, and then take the dot product of those two things. So this is below, and again, remember what we're imagining is the V represents the velocity field of, say, a river. So all the points in the river are moving in a particular way, which, as usual, this doesn't really make sense. And then we're having it go through this surface, which again doesn't make sense because this is a paraboloid going down, so the river is flowing up to some extent, but that's okay. So on this. So let me do another one. Number 11. So let me make this more specific. So the cylinder radius 5 center and the z-axis from z equals -7 to z equals 7 is the this. So here's the cylinder. And this one, unlike the last one, we don't have the parameterization. Oh, and this is just the open cylinder, so it's not closed on the two ends. I'll actually do that in the next part, close on the two ends, and ask how we could then do this. Which means we have to get the parameterization. So what is the parameterization for this thing? So the parameterization for the cylinder, so the x and y would be polar coordinates. So x would be our cosine, and I'm going to use u instead of the usual thing. In particular, here r is equal to what? 5, right? And z is just itself, just any number, -7 to 7. So once we have that, now it's just like the last one. We take the two derivatives. So the derivative of x with respect to u. No real reason. Part of it is just the typical way the text does it. Part of it is, given the thickness of my writing, thetas are probably going to look like dots. But you can call it whatever you want. There's no reason that I'm calling it u here in particular. I lost the 5 somehow. Oh, z equals v. Thank you. Sorry, I missed that question. Well, so the idea is, for this, it's pretty obvious, right? Because that's a circle, so we know we want to use polar coordinates, and we know that r is equal to 5. So this one should be fairly straightforward. And then since there's no restriction on z, z is just z. So there's some ways you could just leave it as z is equal to z. You don't have to call it v. Again, I'm just doing that because of what the text is usually doing. So the idea is there's no restriction on z, so it can be anything, which means it's just a usual variable. And then we take the cross product. And again, let me just do it. Yes. So like that. And then I do put the parameterization into v. So minus y. Oh, because the last component, so here's so I didn't actually write it out, but the parameterization is 5 cosine of u, 5 sine of u, and then v. So therefore, the derivative with respect to u of v, of course, is 0. X. So the idea is, here's our surface. You'll notice it doesn't contain z, which means there are no restrictions on z. So z can be whatever you want. So really, we're just saying z is z, and I'm just writing it as v because that's the typical way this text is doing it, using u's and v's instead of whatever. But there's no restriction on z, so it can be any number you want. And then we plug it in. I should ask, so I'll leave off the limits for a second, and then take the dot product, although the limits aren't going to matter, you'll see, which will get the, and I don't have room to do it, but we're going to do the dot product. So negative 25 sine of u cosine of u plus 25 sine of u cosine of u plus 0. But let me put in the limits anyway. Obviously, we don't need it because it's going to be 0. Right, so u goes from 0 to 2 pi, so that's the inside one. And as it's given, z goes from negative 7 to 7, so b is from negative 7 to 7. So this is equal to 0, pretty obviously. So we don't. So this is actually the question, which I'm going to add in something to this. I'm going to use the same one but add in the ends, and then we'll talk about the normalization, which I kind of messed up a little bit yesterday. So I'm going to use this same one, and we'll see if this works. Is this going to work? Yeah, so this will work. Just, again, the usual way. So here, so this is the R. Right, I just didn't put it together. My underline before that is my parameterization. I just didn't actually write it as parameterization. So it's the 5 cosine u, 5 sine u, v. So obviously the derivative with respect to v of the first two terms is 0. Okay. So anything else? So I'm going to bring this to the next page, and it's going to be the same thing. We're going to again get the flow through the cylinder, except now I'm going to add in the two ends. And this we're going to be able to do two different ways, and it'll answer Jacob's question and what I messed up a little bit last time. So let me do 11 prime. So same type of thing. And this now leads into the next one also, but first let me do it using this sections method, which is what we want to do is now, so we've done the cylinder part. Now we want to do the two discs. So let's start with the one at the top. Okay. And this, unlike the last one, we can just read off the normal. What is the normal in this case? Right, because it's out. And since the top of the cylinder is parallel to the xy plane, normal is pointing straight up. And what I messed up a little bit yesterday is, notice in this case, we're not using the parameterization. We're just reading off the normal. So in this one, we're not actually using a parameterization. We don't have to because it's simple, because it's flat. So we can just use the regular rectangular coordinates And that's why it matters that this is length 1, because our area is just the du dv, or the dy dx in this case. Whereas in the last one, it's not flat. And in that case, the surface area, as we remember, we multiply the flow perpendicular to the surface times the surface area. In the last one, when we normalize, we would take the cross product and divide by its length, but the magnitude of the cross product, but that's also the surface area. So we would multiply that by the surface area. So those two magnitudes of the cross product would cancel. Here that doesn't come in because we're just looking at rectangles, so the surface area is dy dx. So in the last one, we didn't get a length 1 vector, and we didn't want it to because we needed that surface area. In this one, since we're using the dy dx, we do need it to be a length 1 vector. And that's what I messed up yesterday. Well, so here you'll see we're not going to actually need it. But yeah, so if we then made it into polar coordinates, then we'd get the r times dr d theta, right? Okay. So I plug in, and you can see the only one I care about, so I'm plugging the thing. So v is equal to something I don't care, something I don't care, and z is equal to 7. And therefore we're getting the disk at, I'll make it a d plus, because that way it's the one at z equals positive 7 of whatever. Really, it's just a negative y, negative y and x, but we don't need that because we're not using the parameter notation. And then dotted with this. And so if we were really going to do this, we would probably want to do polar coordinates, but we don't do because that's a constant. Therefore, this integral will just be equal to the 7 times the area, and the area of this disk is what? Right, 25 pi. Okay, and then disk at z equals negative 7. What is normal there? Now we're at the bottom of the cylinder. And again, remember that we are looking at the flow out. So it's 0, 0, negative 1. And then when I plug in the z equals negative 7, I get something, something, and negative 7. And you can see I'm going to get the same thing. So this is going to go to, again, the 7 times 25 pi. And then putting it all together, the 0 plus the 7 times 25 plus the same thing. We'll see if I mess this up in the next part. So this is the easier case, which is if it's flat, we don't have to parameterize, and we can just read off the normal. And let's see if that's going to give the same thing. Yeah. Now this one I can do a different way, which we started yesterday, which is with the two ends, I now have a closed surface, which means what can I do? So I can now do the same thing in a second. So what's the last thing we did yesterday? Divergence theorem. So let's do the same thing with the divergence theorem. And in that case, instead of doing it into 3 pieces like we did here, we can do it all at once. So 11 again, 11 prime again. So P is still the negative y, x, and z. And x squared plus y squared is 25, negative 7 to 7. So since it's closed, I forget what I'm calling the two things. I think it was M was the surface and E was the solid. I'll write this down in a second, so I might be reversing my notation. The V dotted with the N, ds is equal to divergence theorem, triple integral over E of the divergence of V dV. So here M is equal to surface, E is equal to solid cylinder. And once you see that this is possible, you can see that really I do want to do it this way, because what is the divergence of this thing? 1, right? Because it's the derivative of the first term with respect to x plus the derivative of the term with respect to y plus the derivative of the third term with respect to z. So it's just z. And since that's a constant, what is that going to give us? Just the volume. And this one is one of the three-dimensional ones you might know, which is the volume of a cylinder is pi r squared h. Pi r squared is the area of the circle, and then the height. And here r is 25, so we have the 25. The height is from negative 7 to 7, so 14. And then pi. And so we can do it all in one step, as opposed to the 3 steps we did in the last one. Okay. So any questions on this? Obviously, if the functions are more complicated, this might not work as well, but here it's pretty obvious that works pretty nicely. So in some sense, we never do, because this here, and the last one, which of course erased, when we got n, that needs, so the normal, in some sense, needs, so here's kind of the full thing. So what we have is we have the m, we have the v of the r, if we're parameterizing, we have the v of the r, and then we have the normal, which officially is this, and then we need, in some sense, do need to normalize it. But since this is no longer flat, the du dv doesn't give us the area, so we need to multiply by the cross-sectional area. Which is, conveniently, the magnitude of the cross product. And so whenever we're doing parameterizations, obviously we can cancel these two out. And so in some sense, we don't normalize. We could, but it would be silly because then we'd have to, after we normalize, we then have to multiply by the magnitude. On the other hand, when we don't parameterize, we want it to be a unit one vector because the dy dx will be the cross-sectional area. So the short answer is, if you're parameterizing, you don't need to normalize because that's taken care of in the formula. If you are doing it in rectangular, like the ends like we did in the last one, then you do need it to be a normal vector. A unit vector. Sorry. Okay. All right, so let's do another one. And you can see these kind of work out that 4, 5, and 4, 6 go together. So mainly I'm just going to do 4.5 ones, just two different ways. So 20. I'm laughing at myself because it's really trying to make everything straight when I'm writing stuff. So similar to the last one, we have our velocity field. We have a surface, in this case, the paraboloid that's going down together with the disk, which closes it off and oriented out. Remember, I didn't remind you in the last one. Remember, in the divergence theorem, those two are equal if we're oriented out. So if we're oriented in, we would put a negative in front when we flip to the triple integral. So in other words, this one is oriented out, so we don't do anything. So looking at it, what method do you probably want to actually really do this, even though this is in section 4.5? Because if you see it, it's really easy. So how are you going to do this integral, which is right, the divergence theorem, because you can see that the divergence of v, the derivative of p with respect to x plus the derivative of q with respect to y plus the derivative of r with respect to z is 0, which means that's supposed to say divergence. Right, so if I don't tell you in particular to use one, then you can use either method. Okay, so let me change the problem. So this is the actual problem. And so really, we obviously should do it this way. If not, we would need to parameterize a paraboloid. And in the background, let me just remind you that there's always the easy way of parameterizing things. It's not necessarily the best, but it always works, which is if you have in the form z as a function of x and y, you can always just let x be u, y be v, and z be that. So there's always an easy parameterization if you have z in the as a function of x and y. So that would probably be the parameterization we use. But as I said, it's silly here. So let me change the problem and just say it is just the paraboloid. Oh, so just let me put it here. Right, because remember, the divergence is the derivative of p with respect to x, which is 0, plus the derivative of q with respect to y, which is 0, plus the derivative of r with respect to z, which is also 0. So we're integrating 0. So this function here is 0. And I'm not sure why I'm calling f here. Okay, so any questions on this? This doing it using the 4.6 method. Okay, so let me change it. Everything might be easy. That's okay. Now I'm thinking about it. So what I'm going to do is do a 20 prime. Still oriented out, but now without the disk that closes it. So how do you think you would do this problem? So we could use the method straight 4.5, which is we can parameterize, take the two partial derivatives, take the cross product, and so on. Or, because we can my 20, that if I close it, it's simple. I can close it. I now know that the integral over m prime is equal to 0 from the last one. So I need to get what is the flow through d. And that's a little bit easier, not quite as nice as the last couple, but not too bad, which is, again, that is flat, so I don't have to parameterize. And what is the normal? Disk at z equals 0. Sorry about that. So that's supposed to be DISC. So what is the normal for the disk? Right, because that's again pointing out. So therefore, the integral of the disk is the dot product of v and here we're not printing. So of the something I don't care, negative x dotted with the 0, 0, negative 1. And I don't get a cut, which means I'm actually going to have to do the integral. I think this came up sort of before. Do this integral, and since we're setting up this way without the parameterization, we don't have to use a parameterization, but since we're doing this on a disk, what kind of coordinate system are we going to use? Polar. Right? So we're going to say this is equal to the integral from 0 to 2 pi. The rate is well, let me do this and then I'll hopefully put it together. So I'm not sure exactly what you're asking, so let me finish and then we'll put it together. So here, when I put in z equals 0, this becomes x squared plus y squared is equal to. So therefore, r goes from 0 to 2. And then x becomes the r cosine theta. We get the usual r, and then dr d theta. And therefore, we're going to get 0 to 5, 1/3 r cubed cosine theta, 0 to 2. I ran out of room, but what am I going to get here? So I'm going to get 8/3 sine of theta from 0 to 2 pi, which is, this is a really boring flow here. 0. Because sine of 2 pi is 0, sine of 0 is 0, so everything's 0. So this is the flow through D. The flow through M prime, which we got in the last part, is also 0. So the flow through M is equal to the flow through M prime minus the flow through D, and everything's just 0. Just a nice boring example. So D doesn't equal to n. This is the normal vector. And D is the disk that closes off this paraboloid, which means it is in the xy plane. So not just parallel, but in the xy plane. So D isn't equal to n. D has the normal, n equals 0, 0, -1. Is that what you're asking? Oh, this is 0. Sorry, that's a 0. So D is equal to disk at z equals 0. Sorry about that. So which now I'm confused. Now I've confused myself. Oh, so M. So this one, in the regular 20, M was the paraboloid with the disk, so the closed surface. In my 20 prime, M is just the paraboloid, so it's not closed. And so I'm saying let M prime be the paraboloid by itself together with the disk that closes it off. So M is just the paraboloid part. M prime is the paraboloid part plus the disk, so the closed surface, which is what we had in the regular 20. Okay, so any other questions on this? Okay, so as I said, pretty much we've been doing both the 4.5 and 4.6, so the basic flow and the divergence theorem in doing these problems. So those are the ones I was going to do. So let me ask any other ones that from either 4.5 or 4.6 that you have questions on or want to look at. Oh. Oh, M prime. So again, M in this part. So in the original, so this is sort of confusing. The reason I have a prime here is this is not the same question as 20. 20 said M is the surface of the paraboloid together with the disk that closes it off. In my 20 prime, I said, no, let's change M. M is just the paraboloid. So it's not closed. It's just the paraboloid. And so I said, so I can use the divergence theorem. I will close it off with the disk. So my M prime in 20 prime is actually the M in the regular 20. So I've made it confusing. I probably should have called it something else. So in this 20 prime, M is the paraboloid by itself. M prime is a paraboloid together with the disk that closes it off in the xy plane. Right. So the idea is, since we're not using we don't need to use the parameterization, because since it's flat, the surface area is just the dy dx, the dA, because we want to multiply the flow in the direction of perpendicular to the surface times the area. So we have to multiply. So that's kind of built in. Whereas when we parameterize, the du dv doesn't give us the area of the little parallelogram. Can't speak for some reason. So we have to multiply by that. So we're not using the parameterization at all. So if it's flat, we don't need a parameterization because we can just read off if it's parameterized or not flat. So if it's not flat, we'll want to parameterize so we can get the normal, because normal will be a function. So any other questions? Okay, so in some ways that's mostly it, but I do want to at least do one example from the next one because you're supposed to have seen this. I forget if you actually use this later in another class or not, but should at least introduce it. So this is 4.7, but it is not on the test. The last one, yeah. So if M is nice, so oriented, which remember mean that I can actually, it's orientable, I can give it an orientation. CCPR is short for closed, connected, piecewise regular, all saying it's nice, so closed so that it's around a solid, connected so we don't have a couple of mean pieces, piecewise are so the derivatives are nice. So pretty much all that just saying we have a fairly nice surface. Because my boundary symbols look like other things, I'm going to give it a name. Doesn't like my C's, which is given its compatible orientation, which I'll explain when we do an example. Then this connects the line integral on the boundary to the flow that's not absolute value or a magnitude, it's just parenthesis, of the curl through the surface. So this is a line integral and this is the flow of a curl through M. So it equates line integrals and flows. So it's just one of these things where sometimes one is easier than the other. But there's a lemma that comes out of this, which is, you'll notice that this says the line integral of a boundary is equal to the flow of the curl. And what that's telling us, and this is the one that, if it was on a test, would be what you would usually use. If you look at old finals, this part comes up a lot. It's fairly straightforward. And the flow of the curl through the two surfaces is the same if they have the same boundary. So I do one example. I'll just do the one example because it's not going to be in the test. And I'm going to go to the next page to show what I mean by that. And as I said, this is the example. So here's just a force field. Let's find the curl. And remember the way of remembering, if you don't, is this is the way to remember it, or the way I remember it at least. You just think of it as the determinant where the first line is the ijk, second line is the derivatives, partial x, partial y, partial z, and then the actual three functions, p, q, and r. And you get that gives this. So here, this is just kind of the setup problem, because then I'm going to ask to get the flow through the surface of the curl of this force field. So r of y is equal to, so in some ways you can see I've made this just to make it annoying. So r of y is x e to the xy Q of z is 3z squared. R of x is y, e to the xy. P of z is x squared cosine of z. Q of x is minus 1. P of y is 0. So obviously, we're only going to be using that third term, because otherwise it can be really messy. So there's the curl. So B. Pretty much the same as the last one. Oh, yeah, did I mess it up? Yeah, you're right. Minus plus. So, thank you. So what we want to do is now find the flow. So find curl of f rho. Okay. So in some ways it's like the last one, except now we have the problem, which is now it's kind of a mess. So we could close off and try to use the divergence theorem, but obviously that's not going to be nice because the divergence of is 2x sine z plus 0 plus 0, so it's 2x sine z, which is not necessarily nice. But what Stokes' theorem says is if we have two things that have the same boundary, then the flow through the two surfaces is the same. So here, what is the boundary? And I'm going to have to put it in the next page. I'll only talk about it here, and then I'll write it in the next one. What is the boundary of this paraboloid? So as you're thinking about it, let's go to the next one. So here we have so what is the boundary of that thing? So I can almost draw this. That thing. So the boundary is that, which is the paraboloid at the xy plane. The boundary is squared plus y squared is equal to 4, the circle. Give me something else that has that as a boundary. The idea is, well, I can fill it in. Right, that's right. D x squared plus y squared less than or equal to 4. boundary. Therefore, the flow through M of the curl, use curl instead of the notation, is equal to flow of the curl, doing a great job here, through the disk. And the disk is flat. So this is now an easier problem. The second integral is the same thing, except instead of M, it's D. So curl of F, yeah, it's really messing up all my writing, sorry about that. So this inside is the same for both. Sorry about that. And so for D, so this is by Stokes. F. So this is in F. So curl of F, the one we just got. Which means instead of looking at the paraboloid, which is curving, I can look at the disk, which is flat. The little thing is, we talk about, I said, this one that is has a compatible orientation, and what that means is compatible by the right-hand rule. So in the background here, since I said this was pointing out, compatible is by the right-hand rule. And here's where I really should have video, which is, so the right-hand rule says, here's my boundary. If I curl my right hand around that, which would be the counterclockwise direction, so if I'm going this way, then my thumb is pointing up. So therefore, for the orientation pointing up, that's compatible with the counterclockwise direction on the circle. Okay. So we do the same thing with the disk, which is, and this is different than the divergence. So again, we have now decided, because they're compatible, that we're looking at the disk in the counterclockwise direction. So therefore, are we pointing up or down for the disk? And the answer is we are pointing up. So if we're using the divergence, we would want to point down because we're doing the outward orientation. And outward is pointing down, straight down, so the 0, 0, -1. But here what we want is the compatible orientation. And so pointing up on the paraboloid is compatible with counterclockwise. So again, wrap your right hand around the circle in the clockwise direction, then your thumb points up. That's why they're compatible. And the same is true for the disk, which is if I'm going in the counterclockwise in the direction on the disk, it's still pointing up, which means I want the vector pointing up. Right. So in this case, we take the paraboloid and instead choose the disk. If we're looking at the curl, which is why it's not necessarily perfect. Right-hand rule. This is right hand, and that's, let's see if I can write it without it messing it up. Rule. Therefore, the integral, we have the curl, which I forget the first two, but I don't care because the last one was -1. And take that with the 0, 0, 1. So you can see I've made it so this is going to be nice. That's -1. Therefore, what are we going to, not too bad time. What are we going to get for the integral? So that's -1, which means I don't actually have to do the integral. It's going to be the area of the disk. So therefore, we're going to get, sorry, I'm really making these last few slides messy. So I'm just going to get -1 times the area of the disk, which is, since there's the disk, radius is 2, its area is pi r squared, or pi 2 squared. So it says if we're looking at the flow of a curl, then as long as two surfaces have the same boundary, we can go from one surface to the other, which means in this case we can go from the more complicated paraboloid to the less complicated disk. And let me do another quick one. I'm not going to actually do one, but just say how we would do it. But so first, any quick questions on this? So here's, let me draw another one of the few I can draw. So suppose here's my surface. Which is, it's 5-sided, I was going to say cube, but not just the sides, without the top. This is M, which is the 5 sides. What is the boundary of it? Sort of the one side, except the rectangle of the top. I let TB top. Then Stokes says that the integral of M of the curl of some function equal to the integral of the curl, and again it's, I'm trying to write it slower, but it's still rewriting everything, on just the top. Well, so here I'm just saying we have the outside of the cube except for one side. So in some ways it doesn't matter which I'm leaving off, but if I'm leaving off the top, then obviously it's the part that's going to be the boundary. So I'm saying we have everything except for that top. So in that case, that top rectangle is the boundary. Whereas if I had everything except for the front, then the front rectangle would be the boundary. And so instead of doing the 5 sides, I could do it on the one side. So anything that has the same boundary, and the boundary is just the edge of the surface, in some sense. So if we're looking at the curl, we can do it that way. But the original one also says, and for whatever reason this never is used on finals, is that it's also a way of going from a line integral to a flow. Because remember, it's if the line integral on a boundary of a vector or force field is equal to the flow through the surface of the curl. So it's giving us two things. It's allowing us to go from rewrite line integrals as flows, and it's allowing us, if we're looking at the curl of a flow, to go from one surface to another as long as they have the same boundary. So this one is kind of a mixed one. So it's not really equivalent to one of the ones from the first three, the 4, 2, 4, 3, 4, 4. But I'm just going to do the one example because it's not going to be in the test. I might still do it tomorrow, but maybe not. So that is it. That's the course. So you have the test review with answers. You'll notice, so the last question is this question, which is not a test. Also, I think it's the next last one, number 6, is messy. It's not necessarily difficult, but it's messy. I wouldn't put anything that messy on the actual test. And as I said, right now I'm kind of leaning for the test being 100 minutes, just like the other two, because it is just another test. But you'll remind me about that tomorrow to see if I've changed my mind. So any quick questions? I think so. Looking at it, it looks long. When I wrote up the answers, it seemed long, so it might be the usual review where the review is longer. So the recorded lectures are in 2 places. So there are lots of questions here, sorry. The recorded lectures are in 2 places. If you go to Collaborate Ultra, at the top there's a kind of a black ribbon, and then underneath it shows where the thing is. On the left of it, there's an icon that has 3 lines. If you click on that, you'll have 3 options, one of which is recordings, and you can go there. And the other place is I also download it myself, put it on YouTube. So if you go into the announcements somewhere, I have the link to the YouTube channel with all the recordings. So the test is, so I'm going to do this again tomorrow, but the test is next Monday at 3:30. So usual thing, let me stop recording, but if you have questions,